Thank you. Hey everyone, how's everyone going? How you all doing? All right, I'm an Aussie, but I've co-opted the term y'all because it's so useful. So today we're talking about protecting data versus systems, as we mentioned. But first, I want to acknowledge a very important religious holiday today. Happy Star Wars Day to anyone who celebrates. May the 4th be with you. So a little bit about me. I'm the founder and CEO at BSidesSF, an American and Australian cryptography and data protection startup. I'm a long-time software engineer and cryptography engineer. I take my coffee with milk, no sugar, please. I'm an Aussie, as I mentioned, but I hate the beach. So now you know that about me. So let's talk about protecting systems. This is a thing that many people in SecOps and security professions think about. But what does it actually mean? Well, when we think about protecting, say, a database, what we think about is applying controls to that database to prevent unwanted access or from data leaking or being exfiltrated in a way that clearly we don't want. But the problem is when we apply policies or controls to that database, it only works for that database. If data moves to another database, say a data warehouse, whatever controls we've set up on the first database don't do anything to protect the data in the second database. So we have to make sure that they're applied to both systems independently, even though they may be saying effectively the same thing. When we think about protecting data, we think about protecting the data directly. So how can we protect an individual value or record, even though when that moves from one system to another, the policies and controls on the system may be different, we can still apply the same controls, same policy to the data itself. A universal protection, if you will. So our goal to achieve this is a granular deny by default access mechanism that works everywhere, that's universal. How might we achieve it? Well, we have some prior art to lean on. Probably one of the oldest permission systems that I'm sure you're all familiar with is file system permissions on a Linux box or a Mac, for example. I can set permissions based on the owner and the group and what things I want that person or the principal, if you like, to be able to do. Thinking about the database, I might want to protect data directly by using something like row-level security. Hands up who's ever actually implemented, I can't really see very well, but hands up who's ever actually implemented row-level security in a transactional database like Postgres. I can't see any hands. If there's any up, maybe one or two, not very many, a handful. It's really hard. It's hard to get right. It's tedious, it's fiddly. And what's worse is it's different from system to system. Postgres does it differently to MySQL or SQL Server. And of course, we have our old favorite, IAM, and its equivalents in the other major clouds. We can police all the ARNs. IAM, I'm sure most of you are familiar with IAM if you haven't spent much time with it, lucky you. It's an effective system, but it comes with a number of challenges as well. So our first challenge, in order to achieve these policies, these controls, the systems must be identity aware. We have to know who the principal is in order to apply the right policies. And so to give a really simple example, if we want to apply a row-level permission in a database, this is using PostgreSQL as an example. Naive example, I wouldn't necessarily have user names in this form, but to give you a sense of it, if I wanted to limit the queries that the current user in the system in the database can perform to only see their own records, then I might use a policy like this. But of course, in order to do that, I need to know who the current user is. And the problem is that most modern applications don't think about identity and the database in that way. Most of the time, the application is the thing that connects to the database, and that has a set of credentials. And so from the database's point of view, it only knows about the application identity and not about the end user identity. So row-level permissions in the database, in that sense, are actually not very useful. We have to have kind of a wide open control set because we have to be able to support in the database all the potential things the application can do. A second challenge, as I mentioned previously, is controls are not universal. And that means quite a few different things depending how you interpret it. Number one is that different systems may have different syntaxes, different mechanisms, maybe even different capabilities in terms of how to apply policies or controls to their own data. So, for example, the Postgres syntax is quite different to the Snowflake syntax, even though it has the same effect. So you've got to learn the two different ways of doing it, multiplied by however many systems you've got to protect. That's error prone. It's operationally inefficient. It's tedious. And of course, there's always the risk that there's another system that you're not aware of, shadow IT, or in the worst case, if the data ends up exfiltrated, then of course, none of those policies are going to help. So my question, which I hope to answer today, can encryption be used to protect data directly? So we could do something like this. We could encrypt every individual field, column, field, row. I call it a cell. I think about the very smallest quantum of data inside a database. How might that help us to achieve our goal? Well, before I try to answer that, I need to do a quick primer on how AES encryption works. So some of you may be familiar already, be a recap for you. Some of you may not be familiar with it, so hopefully you'll learn something from this. So AES, and in particular, AES running in what's called GCM mode, which is probably the most prevalent and NIST ratified. Think what you will of NIST, it certainly plays an important role in this. So we'll take an initialization vector, typically 12 bytes, a plain text, in this case, love coffee, 10 bytes long, and a 32-byte key. So that's a AES 256, we'll use a 32-byte key. We're going to drop those values into an encryption function, the AES GCM encryption function in this case, and it pops out a ciphertext, C, and a tag. And the tag, you can think of, the cryptographers will hate me for saying this, it's kind of like a hash. It's technically a message authenticated code, but it allows us to prove the authenticity of the message, make sure that it hasn't been tampered with. Then we're going to store the initialization vector, the ciphertext, and the tag together, and that collectively is our output. Note that for GCM mode, the ciphertext's output is the same length as the input. Decryption is pretty straightforward. It's just the other way around. We're going to take the IV, ciphertext, and the tag. We're going to put it into a decryption function, and if the force is with me, then I'll get love coffee come out the other side, my plain text. But GCM, AES GCM is what's called an authenticated mode of operation with AES. And that means that we can provide what's called an authenticated associated data. And this is additional information that we include in the computation of that tag, which allows us to prove the authenticity or the validity of that additional data. It's not sensitive, it's not encrypted, so you shouldn't, if you ever start to dig into this, you should never put sensitive data into the AAD, but it's very useful to provide additional context that we can rely upon. And so in this case, I've included, let's say I've encrypted a social security number, 9 bytes long, and I want to include in the AAD to say that this is a social security number. So I'm just going to set that to the characters SSN. An AAD can be any number of bytes long. What's important about the AAD is that it not only proves the authenticity of the message, it also is required to perform decryption. So if I provide the correct, the SSN, in this case, the AAD that was used to encrypt the value, when I provide that to decrypt, everything's fine, it decrypts correctly. If I provide another AAD, the incorrect AAD, the tag is not correct, and so the decryption fails. So that's a really important point. We're going to use that in a moment. Okay, so we've talked about AES GCM. Coming back to our database, encrypting every value, does it answer the problem? Well, we've got a little way to go yet, because now what we've done is turn this into a key management problem. Anyone who's worked with encryption will immediately realize, or within a very short amount of time, will realize that most of the problems with encryption comes down to key management. Thankfully, we have some prior art. We have a few technologies that we can rely on. And one of these is this idea of envelope encryption. So envelope encryption is used by many of the major key providers. It's something we use at BSidesSF as well. And it looks something like this. So let's say you've got a cloud-based key management service. So that might be Amazon's KMS, Azure Key Vault, or BSidesSF Zero KMS, for example. we can, the client that wants to perform the decryption is going to send a data key request to that key service. And the key service is going to use its own internal key that no one ever sees externally to encrypt a randomly generated data key. And that's what we call a wrapped data key. So it's going to return both of those keys. And so to get into that in a little bit more detail, explain what's going on, the key server has a random number generator. It has a managed key. In most cases, that's probably going to be stored in a hardware security module or something like that. And it's going to use that RNG to generate random IV, random data key that we're going to use to encrypt our data. Then it's going to use its managed key to encrypt that. And it's going to pop out a wrapped data key. But think back to a couple of slides previously, this is exactly the same structure as our encryption. It's just that now we're using the encryption to encrypt a data key itself. We're going to return both of those things, the data key and the wrapped data key. So hopefully everyone's following along with me so far. So now to reverse the process, to unwrap the data key, take a wrapped data key, send it to the key service and get the unwrapped version returned. We can just send it over, follow the decryption process like what we went through before. I'm not going to cover it again, and get that data key back. So now we have essentially like a distribution of trust. You can think of a key service like this as a separation of concerns when it comes to how the key is being managed. So now we can enhance the encryption that we're using in the database table by storing not only the ciphertext from the encryption, but we can also store the wrapped data key for the unique data key that's used for every record. It does increase storage space. We'll talk about that. But we now have a unique representation of how each of those records could be decrypted. One last piece of the puzzle, this idea of key commitment. So key commitment is when we're going to combine envelope encryption with this idea of authenticated associated data. I am going to tie all this together at the end, I promise. So we can add one more layer. So let's imagine when we send this request, data key request to the key service, we're going to include some context. We're going to say, this is for record ID 1 and for the field name. And the key service is actually going to use that context, perhaps encode it into a more efficient format, and include it in the authenticated associated data associated with the wrapped data key. It's going to output the result. And now what we have is what I would call a wrapped and committed data key. So that means that data key can effectively only be used when the correct context is provided. We're going to use that to our advantage in a moment. So now when we do the data key request, we're going to send the context and we get back the wrapped committed data key. So how does this play out? So what this means is we have to provide the correct context in order to get the data key that we want. You send through the AAD, the context that it was used to generate, to encrypt the data key initially, and that means the data key decrypts correctly. Then we can use that data key to decrypt the value. So we now have the ability to read the underlying plaintext. However, if anything is incorrect, if the record ID is not correct, or the field name is not correct, then the data key decryption will fail, and thus we can't decrypt the actual value. So hopefully by looking at this diagram, you can start to see something. It looks a little bit like a policy list. This is how we can achieve effectively a policy or attribute-based policy control using encryption and a key service. So access control using selective data key decryption. Can we achieve our goal? So let's take this one step further. So let's now say that our key service is running as a web service. We want to send through some authorization, say a JWT, bearer token, standard stuff, and include our context as a JSON payload. And actually the key service is now going to perform an additional function. It's going to say, or answer the question, can I, the principal, the subject of the JWT, decrypt the name field of record ID 1? Well, because we now have these context values, we can use an ACL list built into the key service to answer the question. Can this user, it's just a lookup table, can this user access this record and this field? And if they can't, the key server will just send back a 401. It doesn't have the correct context, so it can't decrypt the data key. The only thing it can do is send back, sorry, denied. However, if it does have the correct context, it can decrypt the data key, and now it will return a 200 OK along with the data key that that is required in order to decrypt the underlying value. So we've achieved a few things here. We've not only got a centralized policy management system, we have a universal interface, and we also have a way to separate the access. Notice that the key service doesn't ever need to know anything about the underlying values. It doesn't know anything about the plain text. Comes with another side benefit, which is some level of guarantee around logging or recording that that access was made. So if the key service records that a data key was returned, that it was successfully decrypted and returned to the client, we can say more than likely a value was accessed. So there's a potential of a false positive, but there's no false negative. And we will not return the data key if we can't write to the log. So there's some level of guarantee associated with it, which is nice. We can't often get that in systems. So you might be wondering now, if you've been paying attention, where do we actually do the decryption? What part of the system do we process that in? Well, the cool thing is, because there's a universal interface, it gives us lots of options. And some of the things that we think about are, you could do it in the browser. We'll talk more about that in a moment. I suspect there may be some questions around that. If you've got questions, look forward to them. You do it in an edge worker, say Cloudflare or Fastly or something. Of course, you can do it in the application, this idea of application level encryption, or in, say, a database proxy, a proxy that sits in front of your database that performs decryption and encryption operations transparently. So we have a few advantages, and I argue that this, in many ways, achieves the goal. So we have a universal interface. There's one way to check permissions. We don't have to worry about how it's done in Snowflake versus how it's done in Postgres versus how it's done in some other system. It is denied by default because the data is encrypted. If there is an unsupported system, nobody's going to be able to access the data, but at least it's not leaked. And of course, if there is a data breach, somebody takes the dump of the database, or they've got access to the database directly, they're not going to be able to reveal any information. And a third point which I'll make, which may be not super obvious and possibly more nuanced than we have time to cover today, is this idea that the decryption can take place in a semi-untrusted setting. So like in a browser client. If you had data stored in local storage in a browser, and then you had a traditional policy control like an RBAC or something like that, that doesn't make any sense to do that, because the client could just read the data directly from the local storage. Whereas if it was encrypted in local storage and there was a process that had to involve a communication with a key service, then that actually allows you to entertain a model like that. So it opens up other interesting patterns and architectures that are not previously possible. So one more problem. What about queries? If we've got all of our data encrypted in a table like this, what if I want to run a search over my records? I want to look up my name, for example, or find a match, partial match, using the like operator in SQL. Or for that matter, find all people who were born after the 1st of January 2000. Or even sorting. Actually, sorting would work, but it would just give you the wrong sorting, which is not very helpful. So I argue it doesn't work. So how do we get around this? How do we solve this problem? Well, some of you may have heard of homomorphic encryption. In fact, by show of hands, who here has heard of homomorphic encryption? Quite a lot of people. Okay, cool. So for those who haven't heard of homomorphic encryption, it's this idea that you can take an encrypted value and another encrypted value and perform operations on them, say addition, multiplication, or comparisons. It's very, very interesting technology. It's really cool. But as I'm about to show you, has one major problem. So this is a benchmark, and we're going to share a link to these benchmarks at the end of the presentation. So if you want, you can go and have a play yourself. This is for a Rust library, THFERS, which is a fairly recent library and a modern homomorphic encryption scheme. Gives you a sense of some operations that we might care about in a database. So for example, taking a look at the more than comparison between two values, the average time is 191 milliseconds. That's 1/5 of a second for one comparison, which is pretty brutal. What sort of impact does that have on the database? We've got indexes in databases, right? So it shouldn't be too bad. Well, if you have this query, so date of birth more than 1st of January 2000, and let's say my table has 100,000 records in it. It's not a huge number of records, but it's a non-trivial amount. And I have a B tree configured correctly using, say, Postgres, and the planner decides to use that B tree. Well, it'll take around 3 seconds to run that query. However, if I don't have an index, or if for some reason there's a more complicated set of conditions and I'm unable to use an index and we have to do a sequential scan, that's going to take 5.5 hours. I've never had an SQL query run that long, except one time when I was trying to run a very complicated database on a Pentium 3, I think, many years ago. It doesn't happen. You can forget about the concept of real-time queries. It doesn't make any sense when you're using homomorphic encryption, which is tragic because homomorphic is really cool. It's just way too slow. But there is some silver lining. There's a light at the end of the tunnel, if you want to use that euphemism. There's lots of interesting functional and searchable encryption schemes available now. There's been a lot of research even in the last few years. And one example of that is this idea of order revealing encryption. For those that are interested, I'll share links to papers at the end. But ORE is quite cool. So it does one thing. It literally just does a comparison, more than, less than, or equal to. And we've done a benchmark of this. You look at the numbers and you go, actually, that looks pretty similar. But then you realize these are N's and these are M's. So actually doing a comparison using ORE over two 64-bit integers in Rust takes about roughly 200 nanoseconds. So that's 800,000 times faster than homomorphic. So how does that apply? How does that look when we're using it in our queries in our table? So I'm using a B tree, same comparison as before, takes about 4 microseconds. For a sequential scan, obviously the situation we want to avoid in practical databases, but it does happen, we're now looking at 24 milliseconds. So that's pretty reasonable. That's quite fast. So now we have a practical mechanism to be able to provide the kinds of query capability that we need, but over encrypted data as well. So this allows us to consider the idea that encryption can be used as a universal policy control mechanism. So ORE is one example of a searchable encryption scheme or a functional encryption scheme. There's quite a lot of others. And in fact, there's whole categories of different encryption schemes. And if you're really interested, once again, I've shared some papers at the end. There's this idea of symmetric searchable encryption or SSE, structured encryption, things like encrypted Bloom filters, and many others. It's actually quite a ripe field of research right now. So that's it, really. I argue that we've achieved our goal. We have a universal encryption system that allows us to apply policies in a single, using a single method that works anywhere, and through the use of searchable encryption, ensures that we can keep it practical. It works in any database. So I've shared some resources here. You go to github.com/BSidesSF. We'll have a bunch of links there. And I've shared my email here as well. So if you feel like getting in touch and you want to have a chat, ask me questions, tell me where I'm wrong. I'm always open to hearing where I'm wrong. Then please reach out. And thank you very much for your time.
Thank you, Dan. And again, I'd like to remind you, if you'd like to ask a question, you can post it anonymously on Slido. However, we do not have anything right now on Slido. If anybody has a question, raise your hand as well.
This one up back there. Sorry, you're going to have to speak up. I'm sorry, I can't hear.
I'll come to you.
Thank you. I'm an old man now. I can't hear very well.
Can you hear me now?
Yeah, that's great. Thank you.
So if you're using like traditional homomorphic encryption schemes, not the ORE stuff which you just mentioned, with like 100K records, I'm assuming like the noise level would be really high. How do you bootstrap after a certain time, or how do you manage noise? That's not.
Yeah, it's a really good question. I mean, to be frank, I avoid the use of homomorphic encryption in these settings for performance reasons, but you've touched on some other reasons why they can be pretty challenging. So, for example, one scheme, learning with errors, which is very similar to some of the post-quantum crypto that we're seeing come through now, has this idea of noise, as you suggest. I mean, one thing to remember, though, is that that's only really a problem when you're encrypting lots of values in the table. It's not so much a problem when you're doing a query, because you're only comparing one value to another value, then that same value to a different value. So the noise is not really a problem when you're doing a comparison, but certainly when you're encrypting lots of values, it is an issue. So you would have to bootstrap regularly, yeah. But that's just another nail in the coffin for FHE in my view. No worries. Over here. Yeah, it's something I've spent a lot of time experimenting with and trying to make work. So there's a few gotchas. It's achievable. We've actually done it. And the good thing about something like PostgreSQL is you can create like custom operator classes and things like that. So it's actually not too bad. The scheme that we use, for example, the comparison operation relies on nothing more than HMAC. And so we actually just use PG crypto and HMAC. We created a stored procedure and a bunch of custom Postgres classes. It's pretty horrendous, but it works well, and it's been very well vetted. But it took us quite a long time to work out how to do that. Yeah. No worries. I can't see anyone else, so I can't see you, but I can hear you.
I'm up here.
Cool.
If you're using ORE, how does that not end up just being another way to reveal the data? So like I could say, show me all of the records where the date of birth is between January 1 and January 2, and now I've got all those people's birthdays.
Yeah, totally. So you have to think about what permissions or what capabilities you're giving to each kind of actor in the system, right? So one thing that's really important about the different some of the different ORE schemes, in particular, one by David Wu and Kevin Lewy from a few years ago, you actually need a key in order to perform a query. So running queries is a trusted operation. And you definitely don't want anybody that's just got arbitrary access to the database to be able to run those queries. And some of the older schemes, like there's the predecessor to ORE, the idea of auto-preserving encryption, would definitely allow an attacker to run just arbitrary queries even though they don't have key access, which is bad, because then exactly to your point, and that whole problem is what's called an inference attack. And there's a big body of literature on that. The idea of having to have a key in order to run those queries is a really big step forward. But you also need to remember that just the act of being able to run a query is going to reveal some information. So do I get results? Do I not get results? That's information. And actually, some researchers have proven that there is a sort of a theoretical lower bound to the amount of information that can be revealed just by the fact that we want to run a query. So, but all this stuff comes down to whatever your risk model is and how you think about the security of your systems. But certainly there is the state of the art when it comes to ORE addresses like the vast majority of those problems. Yeah, no worries.
Seems like this is all the questions we have for now.
Cool. No worries. Thanks so much, everybody. Cheers.
Thank you, Dan.